Okay, gang, welcome back. Happy Wednesday. We'll start by looking at the calendar and then we'll talk about the tests for just a minute. So today, covering exponential and log equations. Project 4 is on your tables. It is one piece of paper, so go ahead and grab Project 4 right now. As with all the projects, you are welcome to work with other folks, including classmates and people in the math studio and me. So feel free to talk about that project with anybody you'd like. You can see there is not a whole heck of a lot left in this semester. Third test is behind us. That's the last test, not counting the final exam. We've got, including today, 1, 2, 3, 4 days of new material for the entire semester, and that is all. This TBA day is just there in case we had a snow day. I would have a little bit of flexibility in the calendar. It's just going to be 2 review days for the final exam, assuming we don't have a snow day. Final exam is coming up on December the 21st, which is exactly how long from today? 14 days, 2 weeks from today. Wednesday, 2 weeks from now is our exam right here in this room, 1 o'clock to 3 o'clock. This course will be completely in your rearview mirror 2 weeks from now. Coming up, Project 4, like I said, is assigned. It will be due on December 19th. That's the last day of classes. And I will give you one more take-home quiz for you to work on. I'm handing that out, I think, Wednesday coming up. Okay, so thinking about the tests here. So the median grade on the test was a 75. So remember, median again is if everybody were to line up from the highest grade to the lowest grade, person right smack dab in the middle is 75. I'm not sharing that because I want you to think of yourself as being in competition with anybody else in this class. You are not. Just trying to give you a sense of the level of difficulty of this particular test. The high grade on this test was 103. There was a 4-point extra credit question on the back. It's just obnoxious for somebody to get a 103, right? Like, why would you do that? I wrote an answer key. I didn't get a 103 on this test. There was a question where there was a hole in the graph and I didn't see the hole, so I lost some points there. So in terms of moving forward, so some people did quite well. Some people did not do well on this thing. I told you that it was a challenging test, and that was the truth. The fact is, math is cumulative by nature, and so it makes sense that the hardest stuff that you are doing in a math class happens late in the math class. And so, you know, sort of expect test grades to be a little bit lower as you go through. Like, assuming consistent effort on the students' parts, the test grades will decay just a little bit. But if you feel like you kind of fell off a cliff on this particular test, there's 2 weeks left to make a change, and that's enough time to make a change. The final exam is worth 15% of your grade. I promised that those of you who did not do so great on the first test that I would replace that first test with your final exam score if your final exam score was better than your first test. So I'm going to make the same promise here on this test number 3. If your final exam is better than your test number 3 score, that's going to be your way of showing me that you pulled everything together and you got it when it came time to take this challenging cumulative final exam. So here's my offer, just to be clear. Well, if your final exam grade is better than any of your first 3 test grades, 1, 2, or 3, I will replace your lowest test grade. Your single lowest test grade, I will replace with your final exam if that helps you. I'm not going to replace both test 1 and test 3 for anybody. It's just your single lowest one, okay? And so I know some people are looking at a score that they're probably not so thrilled with right now. I'm hoping that this is a little bit more motivation to kind of pull the pieces together before that final exam. That final exam can replace this thing, if that's your lowest test score, okay? So, okay, so the other thing I want to say about the test is that for some folks, this test was quite a bit lower than previous test grades. And I know that people are working in this class, and I can see the time, like I can see how much time you spend on my math lab, and that's not me just being like, you know, like observant. Like I have data available to me on my math lab that tells me how long you are spending on my math lab. So I know that people are working. A while ago this semester, I handed out a 1-page reading called Homework as Assessment, and I said, hey, might consider reading this thing. I don't know how many people did, but I'm just going to recommend it one more time. If you still have it, great. If you need another copy, I can get you one. But the thrust of that one-page paper is that the typical way that students work on math homework isn't necessarily going to lead to the greatest understanding of the material. And that's the goal at the end of the day. The goal is not to get 100% on the My Math Lab homework, because you can do that without learning the material. The goal is to learn the material. And so what many students end up doing, this is not me talking to this class in particular, but just math students as a whole, oftentimes will take a homework problem that's given to them and then go find a similar problem in the notes or in the textbook, or they click the button in My Math Lab that says, show me a similar problem or something like that. And once you've got a model problem in front of you, it's pretty straightforward typically to just kind of follow the same process, right? And that is probably the quickest way to get 100 on a homework assignment. It doesn't necessarily lead to increased comprehension. And the thrust of this one-page handout that I gave you a while ago is that maybe instead of doing that, you view every single homework problem as essentially its own test, standalone test with no resources, no button that you can click, no textbook you can open, no notes packet to go find something similar. You just test yourself on any homework problem, and you struggle and you muddle through, and you spend at least 5 minutes potentially doing nothing but staring at this problem before bailing and then going to try to find not an exact problem, but just some little hint, some push that will get you at least the first step. And maybe you find a problem that's similar, but you don't read the whole thing start to finish. You just cover up the paper and you read the first step. And say, okay, that's the first step. And then you go back to your homework problem, and you do the first step. And then you struggle and you see if you can figure out the next step without going back and reading a similar problem. Now, I know that you all have finite amounts of time available for my math class, which is quite sad because I wish you had infinite amounts of time for my math class. But that's the reality. And so it might seem like this is an unrealistic way to think about doing homework, and it would take forever and a day to do the homework assignments if you really like slowed down and did not seek out assistance until you just sat there and struggled through the stuff on your own. So what I propose, if spending more time on the homework is not an option, and I get that, I'm a realist, is that you just maybe try this idea suggested in the paper and just do less homework. Just accept that on some homework assignments, you're going to get a 75% instead of 100, or a 50%, or a 25%. It might be better in terms of your learning outcomes to get a 25% on a homework assignment, but really know how to do that 25% of the assignment and then translate it to the tests. The homework is worth peanuts compared to what the test is worth. And so really, it's easy to focus on like the short-term gain of, oh, I'm going to get 100 on my math lab assignment, and kind of lose sight of the big picture. It's really about showing, it's about replicating test circumstances and then being able to do well on the tests. Okay, so I think that's about all I have to say about the test. Thank you for bearing with me here. If you have questions about your individual test, I'm happy to meet you after class or before class almost any day. And if you have, if you don't have the article anymore, I can make you a copy. You can just let me know. All right. Okay, one other piece of business in terms of grades before we move on to the new stuff today. So the as you know, any homework assignment you do on My Math Lab that's after the deadline is a 10% off kind of thing. And you can go back all the way to the first assignment of the semester and do problems that you didn't get around to doing, and the penalty is only 10% off. But at some point, I am going to write down your final homework grade from My Math Lab, and anything you do after that point is not getting recorded in my spreadsheet and will not be reflected in your grade. So what I'm doing now is telling you when that point is. I said to you that our final exam is 2 weeks from today, starting at 1 o'clock. I am going to write down your My Math Lab grade at some point after you start taking our final exam. Okay, I promise you I will not record the grade until you start taking the final exam, 1 o'clock, 2 weeks from today. So that means that you have all the way up until 1 o'clock, 2 weeks from today, to do homework and get credit for old problems. I don't know if I'll record the homework grades while you are literally taking the test, or if I'm going to do it a couple of hours after the test. I make no promises as to when I do that, and you're really not going to know looking at My Math Lab whether or not I have done that. So you want to make sure that you do whatever you're going to do by the start of the test, the final exam. Any questions on that? All right, so here we are on page 1, very last math packet I might ever give you. Certainly it's the last one for this semester. So we said we've got 4 classes left of material to do, and this is the first of those 4, so let's jump in. The idea for today is to learn how to solve equations where the variable is in the exponent or where there are logs floating around in the equation. 2 kinds of equations we're solving today, exponential and log. Here's the first one. 2 times 5 to the x equals 50. 2 times 5 to the x equals 50. It is quite possible, so the answer to this one is a small integer. And it is quite possible that some of you have a miracle right now and can decide, oh, I know what x value up there will give me 50. What is it? Squared, right? 2 times 5 squared. That's the answer. Okay, but if we change this not to 50, but to, say, 20, the answer is not a nice integer. The answer is some decimal, some irrational number. And so what I want to do is make sure that we have a process so we can solve it in any case, even if it's not just a nice answer here. So we're going to solve it as if it were not a nice answer, as if we couldn't just stare at it and have the miracle that says, oh, x equals 2, this one's easy. So here's the process. First thing to do is to isolate the exponential expression. That is the thing with the variable in it. So we're going to move that 2 to the other side by doing what? Divide by 2. So we go 5 to the x equals 50 over 2, which is just 25. And now it maybe is really easy to have that miracle because you just say, oh, 5 to the second power happens to be 25. But again, I'm going to pretend that the answer is not obvious. And we're going to give you a technique that will work in any case. So here's the idea. What we are going to do is take the log of both sides. We're going to take the logarithm of both sides of this equation. So I'm going to write the equation again here in black, but just leave a little bit of space in front of both sides. And in that space, we're going to write log. Log of this equals log of this. Now that might look strange the first time you do it, but in the same way that we're allowed to, for example, add 7 to both sides, or divide both sides by 18, we are allowed to take the log. As long as we do it to both sides, we are treating both sides equally, okay? All right, what base did I imply? It's base 10, because I didn't put a number down there. You could put any base you want to, but we're going to choose one of the bases that's on our calculator. Okay, now we're going to use one of those properties of logs that we talked about before the test. On the left-hand side, I've got log of something to a power. Do you guys remember where we can move that power? And plop it right down in the front, and so that's the next step. X comes in the front. I'll put a multiplication dot just so we're really clear. It's x times the log of 5 equals the log of 25. Now we are going to use the calculator in just a moment. Log of 25 is just a number. It's a messy number, but it's just a number. Log of 5 is also just a number. But before we do that, let's write down one more thing. Given that log of 5 is just a number, how do I move that number away from the x? As we divide, because it's multiplication now. So x equals log of 25 divided by log 5. Okay, so I'm going to do the calculation here. First, I'm going to show you the messy numbers on their own. Log of 25 is that. Log of 5 is that. But if I divide these two terrible looking numbers, any guesses? 2. Okay. Now in this one, it was really silly for us to do the game with the logs because the answer was obviously 2. But I can change that 50 to pretty much any other number, and the answer will not be obvious. But this technique will always work. To summarize, when the variable is in the exponent, is when we take the log of both sides. The variable being up there in the power is why logs were the right tool, because what could we do with that variable once it was inside of a log? Before that, we moved it to the front. That is how you get your hands on a power, is you take the log, and then you can use this nice property to bring that power into the front. Next page. I have no next page. You guys have next pages, right? This is the first equation where there is a log in the equation. We are solving for x, and where is the x? It is buried inside of a log. So process is a little bit different from the one that we did before, but the first step is kind of the same. The first step before was isolate the exponential part of the expression. Here we're going to isolate the log part of the expression, which means what can we move? The 2. That 2 should not be here. Let's get it out of the way by dividing both sides by 2. So 4 divided by that 2 just gives me 2. Great. Okay, we've got the log part by itself. Unfortunately, the x is buried inside of a log, and what we need is a way to get our hands in there, right? We need to get it out of the log. So the way that we get it out of the log is to just do the definition of the log. Every log has a corresponding exponential version. What is the implied base? 10 is correct. So this thing just has that same kind of arrow pattern. What to the what equals what? 10 to the, remember this thing? This to the this equals this. 10 to the second equals 5x. Isn't that it? And all of a sudden, an equation that was sort of wrapped in mystery with x's inside of logs is an equation that is trivial, right? Like this one is done. Let's see, this is really just 100 equals 5x, so x is 20. Great. Okay, so again, the thing that made this work, after we isolated the exponential piece, we just used the definition of log and wrote the corresponding exponential equation, and then it was easy, all right? Okay, I think that's good. It bears saying that technically for all of these log equations, we have to check our solution. It's possible that even though we do everything correctly, we get a solution that isn't really a solution, and we've seen that in other contexts where you do nothing wrong and you get x equals 5, but it turns out x equals 5 just doesn't work, and maybe there are no solutions at all. So I'll tell you there is a shortcut. We don't technically need to do the whole thing. X equals 20. All we need to do is make sure that when you take the log, do you guys remember the graph of the log function? That should hopefully look familiar. That's the graph of our log function. Notice that this function gets very close to but does not touch the y-axis and then completely disappears on the left. There is absolutely no picture out there, which means that you cannot put into the log function. I can't put in any x that's out here. So what numbers am I not allowed to plug into my log function? Negatives. I can't plug in any negative. You try it right now. Type in log of -7. The calculator will explode. Shield your eyes. So all we have to do to make sure that x equals 20 is legit is just verify that 20 gives us something positive inside the log. If it happened that we had a negative in there, that would be a problem. So for example, if it said this, log of 5 minus x instead of 5 times x, what do you get when you plug 20 in? -15. No good. So if that were the case, then you would say, oh, x equals 20 is the only candidate for a solution. Turns out not to work, so there's no solutions. All right? So that's all you have to verify, is that you're not taking log of anything negative. Okay, one last example, and then you'll work on the activities. Okay, this is another equation with logs in it. But in this case, there are 2 different logs, so of course it's more complicated than the one that we did before. Here, it is not possible to just isolate the log expression. But what we are going to do is get all the terms with logs in them to one side of the equation, and anything without a log to the other side of the equation. So the simplest way to do that is to add this log base 2 to both sides. So our new equation down here, 2 equals, we had log base 2 of 4x. We are now adding log base 2 of x. Okay, so the issue here is that there are 2 logs. I can handle it if there's 1 log. We had other properties of logs that we talked about before the test. equivalent to log base 2. Matt says this, log base 2 of 4x times x. Right or wrong? You guys remember on that day we talked about all the log properties? We had a property for dealing with the log of a product of things. It's written up here for your reference. This guy says that if you want to take the log of a product, it really becomes two different logs added up together. So Matt just used that property, but going the other direction. We had two logs added together. Certainly we could smush them together and make a single log multiplied inside, right? And so the other day when we were talking about those log properties, I said, hey, we're just kind of like solving math problems, but there's nothing interesting and no reason why we should do this. It's like, oh, there's log properties. So what? So this is why we care about them, is that we can use them to solve equations. We took an equation that had two logs in it and have made an equivalent equation that has just one log. And I can solve any equation that has just one log. So the next thing Matt said was that we might as well smush these two things together inside the parentheses. So that's really 4x squared. And now we're ready to convert that to exponential form. Something to the something equals something. What to the what? Yeah, let me put some arrows here. This guy raised to this power equals, equals that thing over there. So what is it again? 2 to the 2 equals 4x squared. Fantastic. And now we have an equation that we can solve. So this says 4 equals 4x squared. Divide both sides by 4. 1 equals x squared. How much is x? 1. Giovanni? Giovanni says plus or minus 1. It is plus or minus 1. Really easy to forget that. This is something you guys have known for a few months now. The power up there, how many solutions you should be expecting. Plus or minus, there's your 2. Okay, last piece to this one is to make sure that they both work. Remember, the only thing you have to verify is that you are not taking logs of what kind of number? Negative. As long as you are doing logs of positives, it's going to work. So when you plug x equals 1 in here and in here, do you have any negatives inside of a log? No, all positive, all good. When you plug negative 1 in for x here and here, do you have any negatives inside of logs? Yes, you do. So negative 1 is not a solution. So then we will write down after that, reject x equals negative 1, x equals 1 is the only solution. Yeah, Aaron. If that's the goal of the question, then yes, I'll say expand this log, or I'll say contract these logs. But in something like this, I would just say solve the equation, and then in that process, you'll need to realize, oh, I need to condense two logs together. Good question. Okay, any other questions on that? Okay, so the activity starts on the next page. Raise a flag, and I will walk around.